Hi guys, so question number one says cobalt, rhodium, and iridium are metals in the same group. Now, what does the same group mean? It means that they will be found in the same vertical column of the periodic table because that's effectively what a group is. So, here you have cobalt, that's rhodium, that's iridium, they belong to the same vertical column. That is good stuff for us, right? Now, it says the shorthand electronic configuration of cobalt is argon 3d7 4s2. There are a couple of things that you need to know conceptually and theoretically before solving this question, right? And even if it's not tested here, you should know this. Firstly, you need to know that the 4s is filled before the 3d. Why is the 4s filled before the 3d? Because the 4s is at a lower energy level compared to the 3d. Cambridge just writes the 3d first before the 4s because the only reason why it does that is because it wants to club all the subshells based on principal quantum number. So effectively what Cambridge does is it clubs the 3s, the 3p, the 3d together, and then it moves on to the 4s. But Cambridge knows that the 4s is filled first, then you fill the 3d. It just wants to club the same numbers, the same principal quantum number subshells together, right? So that's the reason why the 3d is written first. You could have also written the 4s before the 3d because that's effectively what's happening. First the electrons go into the 4s, then they go into the 3d. Why? Because the 4s is at a lower energy level than the 3d. That's good stuff. We've established that, right? But Cambridge normally just clubs the subshells based on principal quantum number. Now it says the shorthand electronic configuration is argon. What does this argon mean? Well, you need to understand that shorthand electronic configuration actually helps us, condense the electronic configuration, or otherwise we'd have to write the entire electronic configuration of cobalt, but we can shorten it up. What we do is we write the noble gas that comes before cobalt, and then we write the additional electrons for cobalt using the periodic table approach, and I've shown it right here. So basically, if you just look at cobalt is this beauty right here. Now, which noble gas comes before cobalt? Well, the noble gas that comes before cobalt is argon. Now, argon is going to be written in brackets because that's the noble gas that comes before cobalt. And how many more electrons do you need to fill? Well, you need to fill out the 4s electrons. We've already studied the periodic table approach. If you find it difficult, go watch the lectures. So that's the 4s1, that's the 4s2. So the 4s2 fills first, and then you go on to 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7. So we established the fact that the examiner has written the correct electronic configuration, which is argon 4s2 3d7. And this argon, writing this argon means that the electronic configuration of cobalt right here is 1s2, 2s2, 2p6, 3s2, 3p6. That's the electronic configuration which you are telling the examiner by just writing argon, right? Now, the examiner says identify what is meant by argon by giving its full electronic configuration. So talk about the electronic configuration of argon. What is that? It's 1s2, that's 2s2, 2p6, 3s2, and then 3p6, because we realized that the s subshell starts with the number 1, the principal quantum number 1, the p subshell starts off with principal quantum number 2, the d subshell starts off with principal quantum number 3, that's the d block, that's the s block, that's the p block, and the f subshell starts off with principal quantum number 4. So what's the electronic configuration of argon? That's 1s2, 2s2, 2p6, 3s2, and 3p6. Let's write it down. 1s2, oops, my bad, 1s2, 2s2, 2p6, 3s2, 3p6. That's what AR in brackets actually mean. And if you don't know the periodic table approach, or you've not been lucky enough to have been taught that, you can use your simple method, which is what? You start filling the lowest energy subshells first, which is the 1s, then you fill out the 2s, then you fill out the 2p, then the 3s, then the 3p, and so on and so forth. So you need to accommodate 18 electrons. That's how many electrons there are in argon, right? So you fill out the 1s first, that holds a max of 2 electrons, the 2s, then the 2p subshell can hold up to a maximum of 6 electrons, because you know that the p subshell has 3p 3p orbitals. So the p subshell is a combination of 3p orbitals, and each orbital holds a maximum of 2 electrons. The s subshell is effectively the s orbital, right? And then you move on to the 3s2, and then that's 3p6, and that's how I've accommodated all the 18 electrons. Just remember, if you were to move on to the 3D, make sure to fill out the 4s first, then you fill out the 3D, because the 4s subshell is at a lower energy level than the 3D. Always know that. Or if you don't know this approach, you could, if you don't know the logical approach, you could have also written this thing, solved it by doing this stuff right here. The ones that teachers normally teach, you start filling out the 18 electrons in this manner. So because it's the first video for this particular chapter topicals, I'm just making it quick. So I'm teaching all the methods, right? So you're going to fill out this first, 1s2, then you fill out 2s2, then it's 2p6, 3s2, 3p6, and you don't need to fill out the 3D, because that's it. Yeah, that's all you require. Yeah, because we just move till 3p when it comes to 18 electrons. And here even you don't fill out the 3D, you first fill out the 4s, right? For that I'd have to write this stuff right here. So 4s, 4p, 4d, and 4f. So before the 3d, you would have to fill the 3p and then the 4s and then the 3d. Yeah. Now it says the lowest energy electrons in cobalt are in the 1s orbital. Yes, and that's true, because 1s is the closest to the nucleus. The farther you are from the nucleus, the higher energy level you are in, right? So the electrons which are in the 1s, that means they're closest to the nucleus, they have the lowest energy. It says draw the shape of the 1s orbital. It's pretty easy. You just draw a beautiful circle. Oh, my bad. You just draw a beautiful circle. I'll try my best to draw a circle, but yeah, it's actually a sphere. That's what the S stands for. The shape of the s orbital is like the sphere. It comes from the word sphere, but you just need to draw a 2D circle. You're not expected to draw the 3D diagram for it, right? Neither are you expected to show all the 3 axes. Now deduce the number of unpaired electrons in a cobalt atom. Now in order to figure out how many unpaired electrons are there, you need to know the electron inbox diagram. I call it the EB diagrams, right? So if you look at cobalt, if I were to figure out how many unpaired electrons are there, I'll just expand this. So I know that you have the 4s, good stuff. That's the 4s. And then in the 3D, you actually have 1, 2, 3, 4, 5. So you have 5 orbitals in the 3D, because you know that the 3D can hold up to a maximum of 10 electrons, and each orbital holds a maximum of 2 electrons. So in total, you have 5 orbitals for the 3D. Now, 4s2, we fill that out first. And then how do you fill out the 3d7? Well, you know your Pauli exclusion principle, your Hund's rule, you know your Aufbau principle, which is what? That you start filling it up, and the Hund's rule says you first of all electrons singly occupy each orbital when they start filling it up. So it's 1, 2, 3, 4, 5. It will singly fill it up, and then you start to pair it. Yes, so that's 6 and that's 7, because it's 4s2 3d7. It's even written right here, 4s2 3d7. So how many unpaired electrons are there in the cobalt atom? This is unpaired, this is unpaired, and this is unpaired. So how many? You have 3. That's the number. Easy peasy lemon squeezy. Now part B says table 1.1 gives some details about the stable naturally occurring isotopes of rhodium and iridium. Can you tell me the number of protons and the number of neutrons and the total number of electron shells? It's a pretty easy question. How do you deduce the number of protons? Well, either you would have gone into the periodic table and checked it out, or you could have taken the smaller number, because realize that the bigger number is actually the mass number. It takes into account the number of neutrons in, because mass number is the total number of protons plus neutrons in the nucleus of the atom. So always the smaller number is the proton number, no matter how they write it. So that's 45, that's 77, and that's also 77. Good stuff. Now how do you calculate the number of neutrons? Well, from O levels you must have learned this, that you just subtract the 2, subtract the 2, subtract the 2. But the idea behind subtracting the 2 is that you know that 103 is the mass number, and the way you define the mass number is the sum of the protons and neutrons in the nucleus of the atom. And you already know how many protons you have. That's written right here, 45. So it's just a mathematical equation. What do you get? 103 equals 45 plus n. That is the reason why we subtract the two values. So 103 minus 45, what do we get? We just subtracted 45 on both sides. And so after using my calculator, I know that I get 103 minus 45, I get 58, right? And that's written right here. Now I just need to calculate for these. Now it's just a simple way to just subtract the two, but you should know the idea behind why you're subtracting, because now you're in A levels. You need to know the the most basic concepts to be a mini scientist, right? So you subtract the two values, so that's 191 minus 77 for this one, and that's 193, the isotopic mass, minus 77 here. What do we get? I think we get 114 here and 116 right here. Now you want to figure out the total number of electron shells, and without doing anything, without doing literally anything, you could have just gone into the periodic table, check out where rhodium is, and the period that rhodium is in, that would be the number of electron shells. That's how easy it is. So now I'm going to go to the periodic table, and I figured that rhodium, I found out my beautiful element rhodium, and that's right here. Now which period is rhodium in? Well, that's period 1, this horizontal row, that's period 2, that's period 3, that's period 4, and that's period 5. So since rhodium is in period 5, that means it has 5 electron shells. Or what you could have done is that you could have written down the electronic configuration, which would have been hectic. You would have you would have started filling out the electron subshells, and then you would have moved on to the principal quantum number. That would just take a lot of time. So just always go on to the periodic table, check out which period it is in, and you would know that if it's in period 5, therefore it should have 5 electron shells, because the period number reflects the number of electron shells, and vice versa. So you have 5 electron shells. Done? Moving on. Part C says table 1.2 shows the relative abundances of isotopes in a sample of an alloy containing rhodium and iridium only. Yeah, we know alloy is a mixture of metal with other elements. Now it says define relative isotopic mass. Now it's pretty simple. We know that through our theoretical learning. We know that isotopic mass is literally the mass of the atom of an isotope. So it's the mass of an atom of an isotope relative, because we compare it to 1/12 of a carbon atom, where carbon is exactly 12 units. The difference between isotopic mass and relative atomic mass is that when you talk about relative atomic mass, you actually take the weighted average of all these isotopic masses. You take the weighted average here. Here you're just talking about a single atom's mass compared to the mass of 1/12 of a carbon atom. So it's the mass of an atom of an isotope relative or compared to 1/12 of a carbon atom, where carbon is exactly 12 units. Where carbon is exactly 12 units, right? And you could have also defined it like this, that it's like, the mass of an atom of an isotope, and you know what the mass of 1/12 of a carbon atom is called? That's actually called unified atomic mass unit, right? Unified atomic mass unit. Or you would have seen this in even your O levels by the name AMU, which we used to call atomic mass unit, but now you can also just represent it with a U. It's basically unified atomic mass unit. Unified atomic mass unit, right? So you could have also said that's the mass of an atom of an isotope. It's the mass of an atom of an isotope compared to the unified atomic mass unit, which is basically the mass of 1/12 of a carbon atom, where carbon is exactly 12 units. And that's how we get our 2 max. Now it says calculate the relative atomic mass of iridium in the alloy, right? So we just need to look into these two. And how do you calculate the relative atomic mass? It's what? It's the mass number, or you could say the relative isotopic mass multiplied by the abundance. The relative isotopic mass multiplied by the abundance, right? It's basically taking the average. It's the weighted average, summation fx divided by summation f, simple mathematics. So you take the frequency, which is my abundance, and you multiply it with the mass, right, which is your x. So frequency type abundance, frequency, which is my abundance, multiplied by the isotopic mass, and you sum this and this, you sum them then, and then you divide it by the total abundance, which in this case is 15.18 plus 34.82. So how do we calculate it? It's 190.96 multiplied by 15.18, and because it's sum, plus 192.96 multiplied by 34.82, good stuff, divided by the total abundance, which is how much? The total abundance is 15.18 plus 34.82. 15.18 plus 34.82, that actually equates to 50. How do I know it's 50? Because 15.18 plus 34.82, even if you didn't know this, you could have used the calculator. Or I know this because if this is 50, the sum of this should also be 50, because probably it's given in percentage. It's not necessary, but it's given in percentage. And so what do we get if you use your calculators? What do we get? Let me just use my calculator and then I'll resume the recording, because I don't have a calculator on me, so I'll have to pause it again and again. And remember, you have to write the answer in 2dp, right? So let me use the calculator. Now after using the calculator, my mobile phone calculator, I get 192.3528. But if you write this in the exam, you won't get 2 marks, you'll only get 1 mark, because it's specified here to write the answer correct to 2dp. And normally it's also correct to 2dp when you talk about the relative atomic masses, right? Because in your periodic table, you're given these masses correct to 2dp. If you check this out, it's just 1 dp here, but I don't know. But normally it's just still 2dp. That's the accuracy for ARs. So relative atomic mass, that's 192.35. Couldn't care less.